welcome back to part 2 of the transition metal. Okay, so for this part, we are going to discuss about the trends of the transition metals in periodic table. Okay, as you can see, this is the atomic and also physical properties. Okay, we will be discussing about the trends across the period, the trends within the group. Okay, and then there are 4 things that we need to discuss here: atomic size, electronegativity, ionization energy, and also density. So as you can see, this is table 22.2, where it's actually discuss or show you the physical properties of elements from the potassium to the zinc. As you can see here, we have atomic radius, we have melting point, we have boiling point, and also the density. So what happened, okay, to the transition metal trends across the period? As you can see here from this diagram or this picture, the atomic size decrease across period. Okay, means from left to right. Okay, first the potassium and calcium decrease, but other are fairly constant. As you can see, scandium has 162 radius pm, 162 pm, titanium, and then it start to decrease slowly, right? Okay, why this happen? Because the transition metals, okay, have a d inner orbital. So what happened here? It shields the outer electrons from increasing nuclear charge very effectively. So what happened here? It has poor shielding effect. For example, okay, let's say we have a celebrity here. Okay, a celebrity. This is the celebrity. And this celebrity is actually surrounded by his bodyguard here and also here. They are actually known as inner core electrons. Okay, so this celebrity has his own fans. Okay, so in the yellow here, there are actually the hardcore fans of this celebrity. Okay, so what happened? Right, fans are attracted to this celebrity, while the bodyguard here are actually protecting the celebrity from these fans, from all of these fans to approach, okay, this celebrity. So what happened here? The bodyguard start to push, okay, the fans, and also the fans are attracted or start to pull to the celebrity. Okay, for example, let's say this celebrity is actually the nucleus. Okay, this nucleus is attracted by electrons, the outermost electron, and this, okay, it has two inner electron that actually protecting this nucleus from all this outermost orbital. This is what we call the shielding effect. Okay, this is actually the electrons present in the outermost shell. Here, the outermost shell, they actually do not experience complete nuclear charge or complete nuclear attraction between the outermost and the nucleus because of the interaction with the inner electron here. Okay, right. Thus, the outermost electron are shielded or screened from nucleus by the inner electron. So here from this description, you can relate to this diagram. So this is, here is the ionic radii of the transition metals and also the other elements. So if you have the alkali metal and alkaline earth metal, they have tendency to give or to donate their electron. So what happened here? The size of this positive charge will become smaller than their parent atoms. While for this group, at the P group here, they have tendency to receive electron. So what happened to the size? When they receive electrons, they will become bigger than their parent atoms. What about the transition metals? Okay. Alright, as you can see from here, okay, the size of the ionic radii for the transition metals are almost similar or fairly constant from scandium until zinc. So as you can see, this is where we have the increasing atomic number with the reducing atomic radius from left to right in your periodic table for the D block elements. And then other than that, we are going to discuss about the electronegativity. So what do you understand about electronegativity? It's actually the tendency or the capability to attract itself to attract electron to itself. Okay, so what happened here, from left to right, the electronegativity increase across period, but for the D element, they have small change in electronegativity because of what? Because of the presence of the D electron. Then other than that, other than atomic radius, other than electronegativity, we go to the ionization energy. So what happened to this ionization energy across the period? It will rise steeply from left to right, okay, from left to right, and the electron will become more difficult to remove because of the poor shielding, as I have described in screening effect or shielding effect. So this is the description of the poor shielding effect. What do you understand about shield? Shield is actually to protect, okay, or to halang. So other than that, this is the ionization energies for the first row transition metals. Okay, as you can see, this is actually from left to right or across the period, where we have different ionization energy for the first, second, and also third ionization energies. And then what happened to the atomic size? Okay, the atomic size, the trends within a period, it will increase between the period 4 until 5, and there is no increase between period 5 to 6. And what happened in the period 6? Extra shrinkage, because this is where we have the lanthanide series. Then we have the electronegativity, or we call it as En. What happened here? Decrease atomic size from left to right or from across a period. Increase the electronegativity except for the period 6. And heavier atoms, for example gold and also mercury, they exhibit more covalent character, as you can see from here. This is the gold and also mercury. Then these are the values for the electronegativity for each element. So here, okay, you do not need to remember at all. So usually you will be given the value of the electronegativity for each element here. Then here, other than that, we have the ionization energy, or we call it SIE. Okay, so what happened to the trends here from group 3 until group 12? Decrease in atomic size also will increase the electronegativity and the effective nuclear charge, and also it increase ionization energy across the group. And heavier member much larger than their outer electrons, so they are easy to remove electrons. So what is Z effective? Z effective is actually effective nuclear charge, or it's actually the positive charge felt by an electron. And the formula in order to find the value of the Z effective is Z minus sigma. Z minus sigma. So Z is actually the atomic number, while for the sigma is actually number of inner shell electron, or what we call shielding constant. So in order for you to find the Z effective, here for example I have sodium, magnesium, aluminium, and also silicon. This is where we have the arrangement of element across period. Okay, so first one, sodium. Okay, how to determine this effective nuclear charge? For example here, sodium, okay, the atomic number is 11, the core number here is 10, and the Z effective is 1, and the radius is 186. And then we have magnesium, atomic number 12, minus 10, the core electron, we will get 2, followed by aluminium, you will get Z effective of 3, and then last but not least, silicon, 4. So as you can see, when you have increasing number of Z effective, what happened to the atomic size? They will start to reduce. Okay, so as you hear, the relationship between Z effective and also the radius, when you have a larger number of Z effective, your atomic size will become smaller. And as the distance from nucleus increases, okay, from nucleus and also electron increase, what happens? Sigma will be increased and the Z effective decrease, and vice versa. Last one is the density. Density will increase dramatically because of the atomic size become small. So as you can see from left to right, from across period, what happened here, the density increase and then start to decrease a little bit here because of the atomic size. I think that's all for this part 2. So I'll see you guys in part 3. Bye!